Quantum mechanics has a reputation as being a very difficult subject to understand, and in some ways this is deserved. But what I want to do in this presentation is present a more intuitive way to think about quantum mechanics aimed at the high school level. Hopefully this will do away with a lot of the confusion that can plague this subject. In order to make quantum mechanics more intuitive, I'm going to be using two postulates, two basic ideas from which you should be able to reason out and understand most of the major phenomenon of quantum mechanics. So the first postulate is that quantum objects are instantly reformable wave packets, all part of one thing. And the second is that they might instantly reform when they're interacting, depending on how much of them is interacting, according to the Born rule, where probability of collapse to region is proportional to the squared amplitude. Now, this is a presentation aimed at the high school level, so I'm going to be going through some preamble of the basic philosophy of quantum mechanics and waves and wave packets, and then I'm going to try to explore these postulates in depth and develop them, then show how they relate to wave-particle duality and the famous double slit experiment. So if you're already familiar with quantum mechanics, you might want to skip a bit. Otherwise, please keep watching. Quantum mechanics is the physics of the very small. It describes the atomic realm. And in one sense, we understand quantum mechanics quite well because we can use it to build semiconductors and transistors, without which your smartphone would be impossible. We can understand nuclear fusion and nuclear fission, and we can build lasers. Obviously, without a really good understanding of quantum mechanics, we wouldn't be able to build these modern devices. So we understand the rules quite well, we understand the mathematics, and we can exploit it well enough to build this modern technology. On the other hand, there are some things about quantum mechanics that nobody understands. First, there are the philosophical issues. There is an undeniable, unpredictable, random aspect to quantum mechanics. Because of this, some thinkers have questioned our whole notion of cause and effect. For every effect, there is a preceding cause, or so it seems. But because of quantum mechanics, it may be that for some effects there are no causes and we live in a non-deterministic universe. Or it may be the case that we actually do live in a deterministic universe, and for every effect there is a cause, but it is an unpredictable, non-determinable universe. And we just don't know, and quantum mechanics is consistent with either possibility. There's also an undeniable wave aspect to quantum particles, and some thinkers believe these waves are imaginary, just a convenient calculation mechanism. Again, we just don't know. Further, there is the measurement problem. Quantum objects do not seem to settle on a concrete value until we measure them, leading people to wonder if humans are actually needed to get quantum objects to pick a particular value. This seems quite ridiculous, but it is consistent with quantum mechanics to believe that humans are needed for measurement. Then there are the intuitive issues of quantum mechanics. It is impossible to visualize something that is a wave and a particle at the same time. There seems to be no analog to quantum spin in our classical world, and it is baffling to think that electrons orbit the nucleus without really moving around it. It is these intuitive issues I'm going to focus on in this presentation. It seems to me that some postulates, some understandable basic ideas, are what is needed to get a handle on quantum mechanics. So I'm going to present two basic ideas from which you can reason out what will happen in a quantum realm and lead you to a better understanding. The hope is that you can tell these postulates to someone who has never heard of quantum mechanics before, and they can then reason out what will happen in the famous experiment where you send many particles through a double slit, but send them one at a time. I'm not going to resolve any grand philosophical issues in this presentation, just give you a conceptual model from which you can reason out and understand the major phenomenon of quantum mechanics. To do this, I'm going to have to take a stance on some of these philosophical issues. I have to assume that these waves are real and that humans are not needed to make quantum objects collapse. I certainly don't know any better than anybody else on these issues, but I can't proceed without making these assumptions. Whether or not this model is a true representation of quantum mechanics, I don't know, but neither does anybody else. Before getting to the two postulates, I should say a few things about waves. The wavelength of a wave is the distance from peak to peak or trough to trough. The amplitude of the wave is the height of a wave from its middle point. The period of the wave is the time it takes for successive crests to pass a certain point, and the frequency of the wave is the number of crests that pass a point per second. Then there's constructive and destructive interference. When two waves pass through each other, they can interfere constructively to create a bigger wave. If they interfere destructively, however, they can actually cancel themselves out. And you can see that happening in this little animation. An important thing to understand for this presentation are wave packets. Wave packets are traveling collections of waves, kind of like a bag of waves, but that's not the greatest description. They're constructed mathematically by adding together an infinite number of waves of different wavelengths, and when you do that, you tend to cancel out the waves in some regions, but in one region you get no cancellation, and that's the wave packet. This black line in this one-dimensional drawing of a wave packet is called the wave envelope, and that just represents the maximum amplitude that these waves get to as they travel along. This is a two-dimensional drawing of a wave packet, and it's like you're in a helicopter looking at ocean waves, and the crests of the waves correspond to these red lines as the waves travel along. Here's two animations, a one-dimensional wave packet and a two-dimensional wave packet traveling along. Notice that the waves themselves move faster than the wave envelope does. With these facts about waves in mind, let's develop our two postulates and form our intuitive picture. The first postulate is that quantum objects are instantly reformable wave packets, all part of one thing. So let's try to unpack this statement a bit. So quantum objects like photons, electrons, quarks, and so on, they all exist as wave packets in a quantum field. Now, a field is something basic to the universe that permeates all of space. Photons are traveling vibrations in the electromagnetic field. And as they travel along, they tend to form a wave packet. Electrons exist in the electron field, and they also form wave packets as they freely travel along, but they have a bunch of different properties, such as mass and negative charge. And quarks have their own quark field, and so on. So what's common to all these quantum objects, though, is that they are instantly reformable wave packets, meaning these wave packets can instantly change size. And we're going to go into what this means in the next slide. But first, I just should say that when I say wave packets, you have to take that with a grain of salt. These are three-dimensional waves, and mathematically they're represented by a complex number or with a real component and an imaginary component. So they're much more complex than this simple diagram I have here suggests. What do I mean by instant reformability? Well, upon detection, these quantum wave packets can actually instantly deposit all themselves into one spot. So over here you've got a large wave packet coming in. It's going to get detected by this detector screen. No matter how big this wave packet is, all of it will go to one tiny spot on the detector upon detection. Over here you've got a photon split into two, and it's either going to get detected by this detector or this detector. Now suppose it's detected here. That means that whatever is interacting over here, that has to disappear and instantly rejoin with the rest of the photon, or we don't really know what happens upon detection. This is often called collapse of the wave function. Here I'm calling it instant reformability because in some instances these wave packets can actually instantly get bigger. Now, this might seem like it violates relativity because you're getting instantaneous effects, and even if these detectors are separated across light years, you still get this phenomenon happening. But this doesn't violate special relativity because you can't use this phenomenon to send messages faster than light. Now, this isn't all that happens upon collapse or instant reformation. You also have a bunch of other properties such as spin, energy, momentum that quantum objects can have, and they have a range of possible values just like they have a range of possible locations that they can get upon collapse. So upon collapse, you get a new value of spin, a new value of energy, and so on out of the range of possibilities that you have. One last thing to say is that when electrons are detected by a detector screen, they often don't get destroyed, and they can bounce off the detector screen or get absorbed in there, but the electron is often still there. But photons, they will get absorbed into electron and get annihilated or destroyed when they collapse, and they'll give all themselves to one of the electrons. And that's instant reformability. So why does this instant reformation happen? Why does this collapse happen? Well, we don't know, but one thing we do know is that wave packets tend to instantly reform upon measurement when we measure them. For the purposes of this presentation, I'm going to assume that they also instantly reform upon measurement-like conditions when humans aren't looking. And what are measurement-like conditions? Well, that's when wave packets interact, or they interact with a field created by many other wave packets. So how big does it get and so on? Well, here I have a photon hitting an electron, and if the photon is absorbed by the electron, then it'll instantly reform to some new spot, and it'll get much smaller if the wavelength of the measuring packet is smaller than the electron wave packet. So if the photon wavelength is actually very large, this could actually make it instantly get bigger, but most of the time when we're measuring stuff, we tend to make stuff get a bunch smaller. And why does this happen? Well, we don't know. We can't predict where this is going to occur. It might occur here or here or here. We don't know where along the electron wave packet it's going to collapse to, and we don't know when it's going to happen, and we don't even know if it's going to happen at all. These things might interact for a while, but collapse may not happen. So why does this happen? Well, we don't know. As they're interacting, something special might happen, and if it does, then you get collapse. But what that special thing is, no one knows. It seems to be this mystery that quantum mechanics gives us that we can't solve. But what we do know is that we can predict probabilistically where this collapse is probably going to happen based on squaring the amplitude of the wave packet. So if you square the amplitude, it basically makes the wave packet positive everywhere, and the biggest squared amplitude would be in the middle, and that's the most likely spot that it's going to instantly reform to. Basically, these things tend to instantly reform to where most of them exists. But there is a smaller probability that it might instantly reform to somewhere on the edges of the wave packet as well. And this is called the Born rule, where probability of collapse to a region is proportional to the squared amplitude. We can illustrate this Born rule by considering a photon about to be detected by a detector. So a detector is simply a device that is covered with electrons. And electrons are instantly reformable wave packets confined to a region. When the photon strikes one of these electrons, it's going to give all of its energy to them, and that'll promote the electron to a higher energy, and we can read off a detection from it. So which electron is it going to give all of itself to? Well, since the squared amplitude is highest in the middle, it's either going to most likely give itself to this electron or this other electron. There's a smaller chance that it'll give itself to this one or this one because the squared amplitude here is still not zero. But this is not the whole story of the Born rule. The question you can ask is, what happens if only half of a wave packet hits a detector screen? What's going to happen? Well, half the time you're going to get a detection, and half the time you're not going to get a detection. So if only part of a wave packet is hitting a detector, you may not get a detection. But if all of the wave packet is hitting a detector, then detection is guaranteed. So if you split a photon into two, and half the time you get a detection on this detector, and half the time you get a detection on this detector, what if you remove one of the detectors? Well, you still get 50% of the time detections over here. What this means is that if you fail to get a detection here, whatever is interacting with the detector has to disappear and presumably rejoin the other half of the photon at some point. So this is just a subtle point about the Born rule, but it's important to emphasize for what follows with the double slit experiment. So whether or not collapse happens depends on how much of the packet is interacting. So now we have two postulates to help us understand quantum mechanics better. First is that quantum objects are instantly reformable wave packets, all part of one thing. And the second is that they might instantly reform when they interact, depending on how much of it is interacting, according to the Born rule, where probability of collapse to a region is proportional to the squared amplitude of the wave packet in that region. Now that I've presented these two postulates, let's look at what's known as wave-particle duality. So, quantum objects have a wave nature in the sense that they are traveling vibrations in a field. They are waves. But they also have a particle nature in the sense that the wave packets are all part of one thing. No matter how big a wave packet is, or if it's split into two or more, when one part of it successfully interacts and instantly reforms, the whole thing has to instantly reform as well. Kind of like if you have a tiny particle and you hit the side of it, well, the whole thing has to react to that. So they're part of one thing. In that sense, they're kind of like a particle. What's often said about wave-particle duality is that quantum objects have the properties of both waves and particles at the same time, which is true enough, but a very confusing thing to say, and it almost seems like a logical contradiction. So instead of saying that, I think it's important to say in what sense quantum objects are like waves and in what sense they're like particles. The sense that they're like waves is that they are waves. The sense that they are like particles is that they're all part of one thing. So quantum objects also have some more particle-like properties. They have ballistic properties, so when you scatter a photon off of an electron and the electron quickly re-emits another photon, energy is conserved and momentum is conserved, and you treat this a lot like you treat the collision of two cannonballs. Also, these quantum objects are often small, and in that sense they're like particles too. No matter how big the wave packet is, when you look at it, it suddenly becomes extremely small. So that's another way. Also, some quantum objects can have mass, charge, and spin, and all of these ideas are most easily associated with the idea of a particle. However, I think they all can be associated with this instantly reformable wave packet idea. So one way to sum up what I'm saying about wave-particle duality here, I guess, is that there is no little ball. There is no tiny little objects mysteriously being pushed around by a wave packet. Instead, these are instantly reformable wave packets that can get quite tiny. Now let's apply these two postulates to the famous experiment where you send a bunch of quantum particles through a double slit, but send them one at a time. What will happen given our two postulates that we've already talked about? Well, if you have single quantum wave packets entering the double slit, first question is how big are they? If they're smaller than the slit size, then if they make it through, what you'd expect to see is that a bunch of detections would happen here, and there you go. But it wouldn't be very interesting. More interesting question is, what if the wave packet is larger than the slits, and the wavelength is on the order of the slit size, and it's able to pass through both slits at the same time? What do we expect to happen then? Well, actually, given what we said about the Born rule, we'd actually expect that most of the time it wouldn't make it through, and this is exactly what happens. This wave packet is interacting with the electrons on the outside of the slits material, and it's going to interact with them and probably collapse or get reflected because of them. But some of the time it'll make it through because of these two small holes. If it does make it through, then we'd expect it to interfere with itself exactly like a water wave does when it goes through two slits. So here's a drawing of a 2D wave packet going through, and I've tried to illustrate that in some regions it's going to be canceling itself out along these dotted lines here, and these correspond to these dark regions in this slit pattern here. And in other regions, like right here and right here, it's going to have an amplitude of constructive interference, and it's going to have a non-zero amplitude there, but a zero amplitude in these other regions. Okay, so now it's going to go through and hit the detector screen. What do we expect to happen then? What we'd expect to happen is that where you have zero squared amplitudes, such as here and here, you're not going to get any detections there. It's not going to instantly reform to those places. But where you have non-zero squared amplitudes, such as here or here, that's where you might expect to have a detection. Now, I've put this into a crude animation that you should be seeing here, where you get the wave packets going through the double slit, and then they instantly reform to one of the spots where they're constructively interfering on the detector. They give all of themselves to electron here, an electron here, or electrons over here, but never in between. And if you do run an actual experiment with electrons or what have you, you can see this pattern accumulate over time, and if you send a lot through, you can see the pattern quite clearly. So if you send them through at a rate of just a few every second, it'll take a while for you until you can see this pattern. But if you send many through per second, you can see this pattern accumulate much quicker. And if you have a laser beam with many photons, this pattern should be visible to the naked eye. So with our two postulates, we can basically deduce what's going to happen as you send wave packets through the double slit one at a time, which makes me think this is a much better way to present quantum mechanics. Now, there's still a lot of mystery in quantum mechanics, but the mystery is now in the postulates, not in the results of applying those postulates, which I think is much better. In the interpretation of quantum mechanics I just gave, you have a wave packet larger than the slits going through. But in other interpretations of quantum mechanics, there's kind of an insistence that these little particles are actually like little tiny billiard balls, and they go through the slits and somehow mysteriously form a double slit pattern because of the influence of a wave function. So in that interpretation, you're inclined to ask which way the particle went. Did it go through this slit or that slit? Whereas in the interpretation I just gave, you're not inclined to ask that question. So people have done experiments wondering if these things are really like tiny little billiard balls and which slit do they actually go through. Maybe we can figure it out. So in these which-way experiments, you're sending electrons or something like that through the slits, and of course you get this sort of observed pattern we just talked about. But if you put a detector that tries to find out which slit the electron supposedly went through, you end up ruining the pattern and get this pattern that is reminiscent of just throwing baseballs through two holes, and you get a bunch of detections here and a bunch of detections here instead of the detections here, here, and here that we've seen already. So how is this working? Well, the thing is, how do you do this? How do you detect which slit the electrons go through? Well, you have to do something like this, where you bombard the slits with, say, something like weak photons that will interact with the electrons. And when they interact with the electrons, what happens? Well, the electron wave packet is passing through here and here through simultaneously, and these photons are interacting with it here and here. Now, if the photon successfully collapses the wave packet right here, you'll get the wave packet to shrink to this region. If it collapses it over here, then you'll get the wave packet to shrink to this region. And then once the photon collapses the wave packet, it will then get reflected into one of these detectors, and you'll get a detection saying, aha, it went through here. So as you can see, once you've shrunk the wave packet down like that, it doesn't interfere with itself anymore and just proceeds on to the wave packet making a detection here or here. And so you basically ruin the wave observed pattern that we've seen before and instead replace it with this pattern. And in this interpretation, this is basically totally understandable. Okay, so we're hitting the screen in line with the slits as if there's two billiard balls, but really we're just instantly reforming the wave packet and forcing it into a smaller size so that it doesn't interfere with itself anymore. In other interpretations of quantum mechanics, this which-way experiment is considered very strange and weird, and quantum mechanics is this big mystery sort of thing. But here we can understand why this happens and actually deduce that it happens with our two postulates. I thought I would end this presentation by saying how quantum mechanics is usually thought about. So physicists talk about wave functions, and no one has talked about instantly reformable wave packets before. That's kind of my invention. So a wave function is thought of as a probability wave with a probability density based on the squared amplitude. And these wave functions collapse, and they give you the probability that you'll find your particle in a certain state. And there's a lot more possible states going on than just position. You could have possible values for spin, possible values for energy, momentum, polarization, and also position, and more things as well. And the wave function can give you the probability of finding these things. So that's the way physicists usually think about it. Also, I've been talking about it in terms of waves propagating through space, but waves can also propagate through momentum space and come up with a lot more values than just what I've been presenting about, mostly about position. So I've been using a different terminology in an effort to make this more intuitive, and I hope it helped. And I'd just like to acknowledge where I got the images and animages that I didn't make up myself.